Now let us estimate the pressure drop in case of flow through a slit for non-Newtonian fluids. Okay, so now let us recollect that what expression we have got for V average. So V average is equal to n plus 1 by 2 n plus 1 into V maximum. So that is actually n by 2 n plus 1 into delta V by KL to the power 1 by n, and then delta to the power n plus 1 by n. Okay, so n by 2 n plus 1 delta V by KL 1 for n into delta L to the power n plus 1 by n. So this is the expression for V average. So now we'll have to recollect, actually see what we have done in case of slit flow for Newtonian fluid. So just to for a quick refreshing of your idea, let me just say, you see, tau W, tau value at the interface is delta P by L into half thickness. Okay, and for Newtonian fluid, so we have estimated, again if required actually you can visit the earlier video. So V average is equal to delta P by 3 mu L into delta square. So now what we do, tau W means is shear stress at the wall. So we are interested to have an expression for shear rate at the wall. Okay, so now this is for our, let us say, mathematical manipulation. We are doing it, this particular factor we are dividing by this factor. So then we get a value of 3 mu by delta. It means tau W is equal to 3 mu by delta into V average. Now if we take out mu, then we get 3 into V average by delta. Now you see, its name is shear stress at the wall, and this is coefficient of viscosity. So if we apply this Newton's law of viscosity at near the wall, so then it means this is shear stress, this is coefficient of viscosity, so it means this is the shear rate near the wall. Okay, so or indirectly you can call it, you see, what is the value for mu then, or by knowing the behavior of fluid near the wall, how exactly one can estimate value of mu. Mu is equal to tau W divided by 3 V average, the factor of 3 multiplied by V average by delta. Okay, so now this principle we are going to use for non-Newtonian fluid also, so that we can get some representative parameter similar to mu, which is the ratio of wall shear stress to wall shear rate. And then actually see, we can compare there wherever actually we have estimated this Reynolds number or friction factor, so what value of mu should be taken there, or representative viscosity should be taken there. Can we take this consistency coefficient or flow behavior index directly, or a factor of that? So that is what actually we are recollecting. Tau W is equal to delta P into delta by L. Okay, delta P by L is the actually pressure gradient, and that is the wall shear rate is 3 V average by delta, and thus what we can say is that this wall shear stress is equal to mu into wall shear rate. So now for flow behavior or flow pattern or velocity of this non-Newtonian fluid through a slit, so from this equation we get, you see, delta P by K L to the power 1 by n is equal to this multiplied by delta to the power 1 by n, and this particular factor delta is taken out. Okay, this delta part is broken down, and it is equal to 3 V average. Okay, so then is it from this equation? Okay, so this 3 and this 3, Actually, it was not there in the original expression. We are introducing on both the sides so that we can get a expression similar to it basically. So delta p by L into delta 1 by n is equal to k to the power 1 by n and this particular factor and 3 times of this particular factor. So then taking power of n on both the sides, so delta p by L into delta, thickness delta, is equal to k to the k and this particular factor and this factor to the n. So then what we can see that if we try to compare it with this expression, this is basically see delta p by L into delta k prime into this particular factor to the power n. So now this is actually power law equation. Now see, for this is the shear stress, this is the k prime, not exactly k prime is this particular factor and this is shear rate to the power n. However, if we compare to Newtonian fluid, actually Newtonian fluid is the ratio of this particular factor divided by this shear rate to the power 1 only, not n. Okay. So then if we compare these two, then we get k prime will be there is this divided by this thing to the power 1 only. Okay, so when we take it out this side, that power of 1, so then it is what is remaining is k prime multiplied by this particular factor n minus 1, since it 1 is what is taken out. Okay, so then this is the generalized coefficient of viscosity for Newtonian fluid in slit flow. So that is k prime to the power k prime into t to the power n minus 1. So you can recollect in earlier case when it was a pipe flow, it was a to the power n minus 1. Then after getting this generalized coefficient of viscosity, how we define Reynolds number? Reynolds number will be, we can say that mu equivalence we can write. You see, V average into rho means rho into hydraulic radius. Hydraulic radius is 4 times of the half thickness divided by equivalent expression for a viscosity coefficient. Okay, so now when we substitute it, then we get this particular expression. Numerator remains same, denominator actually we are actual substitution. Then after simplification, it becomes, this is again this is similar to earlier one, 4 times V average to the power 2 minus n, your thickness or representative distance to the power n, and this is rho, and denominator is k prime to the power 3, k prime into 3 to the power n minus 1. So now this factor's name we have said already that is the generalized coefficient of viscosity. So then you see Reynolds number is 4 multiplied by half thickness to the power n multiplied by V average 2 minus n and then rho divided by generalized coefficient of viscosity. So after we know this Reynolds number, then we can very easily estimate the friction factor, or we can apply for the estimation of friction factor the other option, that is the wall shear stress divided by kinetic energy. So this turns out to be 2 into delta P and twice delta W divided by 2 WL. Now here little bit simplification is done. Okay, so this turns out to be, actually this we can compare with the earlier derivation for Newtonian fluids, where actually we have highlighted that we are going to get an expression when the width of the slit is quite great as compared to the gap between it, or the let us say height of the slit. Okay, so W is quite large as compared to delta. So then this is the means approximately equal to this by F, and then after simplification we get this particular expression for this term. So this term again we can get by this one, which is equal to 24 divided by Reynolds numbers generalized. Okay, so now after we get the value for F, then pressure drop can be very easily computed by using that expression 4FL by D into half rho V square. Therefore, there we'll have to note that actually this D, we'll have to say that actually that is the height. That's all. We are concluding here. Thank you.